Good evening, everyone, to our Triple N talk today, the last one before the new year. I have here with me today Eva Gerold, Professor Eva Gerold. She's from the Chair of Non-Ferrous Metallurgy at Montanuniversität Leoben, so I'm sure she's a familiar face to you by now. Still, some quick introductions. Eva Gerold is not new to Technical University of Leoben. She studied here also process engineering and industrial environmental protection, if I'm not mistaken. And she afterwards worked as assistant and also as lead in projects regarding lithium-ion batteries, recovery of critical minerals. Also came all the way up to senior scientist, and now she is professor. Yeah, I don't want to say much more now, and I ask you for your presentation, please.
Yeah, thank you very much for that nice introduction. Yeah, ladies and gentlemen, welcome to my talk today, From Cells to Cells, a microbial recovery of critical metals from spent lithium-ion batteries. So I'm very happy to be here today and give you a few insights on biometallurgy, actually, a new field of metallurgy we are currently working on. So let's start into lithium-ion batteries, but at the very first stage, we need to understand how is the structure and the function of a lithium-ion battery and understand how to recycle them, of course. So in general, we have a positive current collector, a so-called cathode. This cathode is in general made out of aluminium and of a cathode active material. There we have different ones, and I will come to that in a few minutes in a little bit more detail. Then we have a liquid electrolyte in general, a separator made out of plastics, and on the anode side we have a negative current collector generally made out of copper, and the anode active material. In generally for lithium-ion batteries we have mainly graphite or silicon graphite composites. And to make it not too easy to us, we also have several different shapes of lithium-ion batteries. So you might know the small ones, but there are also cylindric ones, there are plate-shaped ones. So quite a lot of form factors also to have a look on if you go into recycling, into sorting, into dispatching out of a bigger module. Well, and that actually leads me to the cathode active material, because this cathode active material actually describes the battery technology behind. And there are several ones that are used currently, but I will just talk about the two most important ones already now, but especially in future. And these are the NMC chemistry, so lithium nickel manganese cobalt oxide, and the LFP chemistry, lithium iron phosphate. You can see for the NMC here that we already have more or less worldwide approximately 50% market share for NMC batteries, and this is predicted to keep quite stable within the next 10 years, more or less. What we can see here for LFP batteries, we currently have more or less a third of market share, and also this is going to be a little bit more in 2034. But please keep in mind that then there's another LFP-based chemistry. It's LFMP, it's lithium iron manganese phosphate. It's just a little addition to this LFP chemistry, and actually you can count this together. So if you have a look here, it's well about 40% together in 2034. That means if we look at this chart here, in 2034 we predict that more or less LFP and NMC will be the most dominating battery technologies for lithium-ion batteries on the market. And of course, the question arises, why is it like that? And actually, there are a few parameters we need to consider. For NMC batteries, we have a cost factor of approximately $100 per kilowatt hour. This is just a half for LFP batteries. That's mainly because of the materials inside, because especially nickel and also cobalt are quite expensive metals in comparison to iron and the phosphorus content on the LFP battery side. But there are also other parameters that are quite important in batteries, like the density and also the specific weight, of course, because especially for EVs, so for electric vehicles, the weight of a battery is, of course, important. And what you can see is that NMC batteries have a higher density, so also a longer range if we talk about electric vehicles, and have a lower weight, what also means a higher range or a longer range in comparison to a LFP battery. And that means there are two different approaches, and this is also coming into different applications. So NMC is especially very famous for its EV application. LFP is also used partly in EVs, but especially in home storages, battery storages for industry, but also like in smaller vehicles, like in e-bikes or in scooters, because there the weight is not that critical. Well, and if we look to cathode active materials, or why do we look that specific on that? It's because the material makes up quite a lot of the costs of a battery, and that's why also this high quality recycling of materials out of batteries is that important. Well, and that leads me a little bit to the material side, just to have a look on that. And what we can see here quite clearly is that different materials are critical. Copper and nickel are at least strategic, and they are mined more or less all over the world. There are hotspots like the cobalt from Congo or lithium from Argentina and Chile. But the main point also on this chart is that there is quite high mining of lithium and also graphite in China, but especially the treatment and the refining of the materials for CAM production, so for cathode active material production, is more or less done for up to 80% over all cathode active materials in China. So refining is a big thing here. And what we can also see here on the right side of the slide is that the material demand is still growing. So from the baseline of 2025, we expect a quantity of graphite to be needed in 2035 3 times like in 2025, sorry. This is also true for nickel, it's true for copper and all the other battery materials. So we will need quite a lot of materials, critical materials also to produce our batteries. We need for our transportation, of course, but also for energy storage systems. And that means recycling is going to be more and more critical. I've just brought 3 examples with me for a short look on supply and demand currently. And what we can see here for lithium, we still have a rising demand within these yellow bricks here. And we also have currently a quite sufficient supply, what is a good thing. So we are not running out of raw material, of course. We can also see that for cobalt. It's like to be a little bit more critical with graphite. And that's also the point why graphite will be one of the most critical battery materials in future. Well, and then always when I start talking about recycling, the question arises, why don't we have any big recycling companies or industries here in Europe. And actually, well, it's a good message for our for all the consumers, because batteries are lasting longer than everybody expected here. You can see that here on the end-of-life battery lifetime ramp-down curves. So for consumer electronics and micro-mobility, batteries are lasting like for 5 to 6 years. For large transport systems, it's up to 13 years. For EVs, up to 15 years, and for energy storage systems, up to 20 years. And actually, the calculation was way lower. You might remember there were some reports about EV batteries lasting for 8 to 10 years. That was for quite a long time the most cited time ranging for a battery, and actually it's like 5 years more. And that's the point. We have expected the scrap wave for end-of-life lithium-ion batteries to reach Europe like in 2024, 2025, to have enough material for running industries, because of course you need to run an industry and recycling industry for 24/7 and not only for 2 months a year. And well, and because of these longer lifetimes of batteries, the scrap wave moved a little bit to 2028 to 2030. So we expect a bigger scrap wave in that time frame. And you can also see that the amounts of end-of-life batteries in 10 years are way higher than they are currently or they were in 2024. And one main point is, very often I also get the question, why does China then have this big industry in battery recycling? And of course, they already have quite a bunch of end-of-life lithium-ion batteries, because they used it for EVs up from 2010, 2012. And so the first EVs are now at the end of their life, but they also have the production of the batteries, and of course they also have the production scraps. And actually for battery production, there is up to 20% of production scraps, and you also need to recycle them. And that's the point why the industry in China is at a very other level than it is in Europe. And that brings me actually to the battery value chain. So, of course, we start with mining to extract the materials, and do refining to mineral concentrates. And out of these concentrates, we can produce cell components and get that cell components to the whole cell production. Afterwards, we have an assembly to stacks and to the whole battery pack, and then we get to application. In a perfect world, we have this recycling loop back to cell components to reintroduce recycled material to the cell production. And actually, China has built up all of this battery value chain. Europe hasn't, and that's a critical point, because if we work heavily on recycling, we also need to work heavily on all of the other points of the value chain, because you cannot close a loop if there is no loop, actually. So we also need to increase our primary production of lithium-ion batteries. Well, and I will not go into detail about regulatory requirements in battery recycling, but there is a quite important point on that, because very long there was no sufficient regulation on this, because battery recycling was not regulated on an element-specific way. And that's the main point. The new battery directive was released in 2023, and it says that we need to recover specific metals at a specific rate. So like you can see here in this small table up there, we need to recover cobalt, nickel, and copper of 90% and also 70% of lithium. And the further thing we need to consider here is that we also need to implement recycled contents in new batteries. And that means we need to implement 12% of recycled cobalt out of batteries into the production of new batteries. And so that means we need high quality recycling. We cannot only recycle the low quality things and get it out to metal industry, for example, for alloying. We also need to do high quality recycling to get back to battery industry. And that is especially also important for in regard of the battery passport, because this battery passport is a storage of all this information, like the recycled content, also the cathode active material, all the chemistries, all the usage of the battery. And that means this is a very important thing to be developed. It's currently under development, actually. There's a lot of discussion ongoing on this battery passport, but just to have it mentioned here within this presentation. So, of course, arises the question, why can't we just use primary metallurgical processes for the recycling of end-of-life products, and especially for the recycling of lithium-ion batteries? Because there is quite a lot of metallurgical know-how and there's quite a lot of metallurgical processes available. And so this metal wheel you can see here explains it actually quite well. In this bluish inner circle, you can see the carrier metals, these main metals of this raw material, the bulk metals. On this outer circle, you can see the co-elements that are also have considerable own production within these main materials and are also mined. On the white circle, you can see the co-elements that have no or quite limited dedicated production here, and on the outer circle that are co-elements that end up in residues in general and are not co-extracted with the main metals in this bluish circle. And if we look to all of the different raw materials, we cannot find any system where you have cobalt, nickel, manganese, and lithium together in one raw material. So that means we are not used to have a process that can cope with this materials mixture. And that's the point why we need new processes on that. And well, so that brings us actually to how to recycle batteries. And the very first stage is, of course, the collection, because we need to collect our batteries to get them to recycling plants. A very big thing, because, of course, there are missorted batteries very often. Also, batteries are thrown into household scrap, and that's quite a big problem. You might already know. After the collection, we go to pre-treatment, and there are various combinations possible, like with sorting, discharging, deactivation. That could be done thermally, that could also be done manually. At least you have a shredding very often at the end of this process part, where you can do separation of the ferrous and the non-ferrous metals in there, so the conducting foils are separated, and also the casings are separated, and of course also the plastics. And on the other side, you get out the black mass. And the black mass is actually a black powder containing all the cathode and the anode active materials and a bunch of impurities, actually. Black mass is a very inhomogeneous material, and it's also very different if it has undergone a thermal pretreatment or not. So here you can see a non-pyrolyzed black mass. You can still see cathode materials sticking together. And here you can see a pyrolyzed black mass, so we're thermally pretreated black mass, which looks completely different, very scattered, and where you also find like oxidic but also metallic particles in there. So it's not a defined residual material. And if we have a look to the composition, We can see here at the upper side of this table the sum of the cathode and anode active materials, so nickel, cobalt, and manganese, and lithium, and graphite and silicon from the anode side, of course based on an NMC chemistry battery. But then the bad boys are coming, so like the inorganic and the organic impurities. The aluminium and copper residues are coming from the iron collector foil. Then we have some iron impurities. We have quite a lot of fluorine in there, actually originating from the salt, so from the conductive salt or from the binder material BBDF. We have also halogens in there, so other halogens than fluorine. We have phosphorus in there, originating from the conducting salt once again, or from missorted LFP batteries. And there's a bunch of trace metals like titanium, zirconium, also calcium and magnesium from fillers, and also like cadmium and zinc from missorted batteries. So you can see quite a bunch of different materials. And then we also have organic materials in there, especially binders and solvent residues up to 10%. Of course, very dependent on the pre-treatment of your black mass. If you have a thermal treatment, the organics are quite low, so below 1%. If you don't do any thermal pre-treatment, and that's actually the way in Europe it is done quite often, you still have up to 10% of organics in there. Well, here is just a very short view on the thermal pre-treatment that is studied also at our university. So here we have a rotary kiln for pyrolysis. So we take these batteries, we do discharge it, we do shred it, and then we go to a thermal decomposition. And what we can see is that we have quite a lot of different gases, but that we can have an efficient separation of the foils, that we can have an efficient separation of the organics. But of course, there are some pyrolysis residues we also need to deal with. Yeah, coming back to the recycling, after we now know what our black mass, our input material is, we need to go on metal recovery, so to metallurgy. The first option is pyrometallurgy with a quite high technological readiness level, where you smelt your black mass, you produce an alloy composing out of cobalt, nickel, and copper mainly. Manganese and lithium is mainly slagged, and actually that's the biggest problem in this process, because you have quite low residual lithium contents in your slag, approximately 1 to 2% actually, and you could leach the the slag and extract lithium, but this is currently not economically feasible. But if you remember the regulatory requirements, we need to recover lithium to 70 and up from 2030 up to 90% of lithium. And so we need to do something with the lithium, and that's why pyrometallurgy is actually not the way to go currently in Europe, but hydrometallurgy it is. In hydromet, we extract the metals from the black mass with acids. Basically, in many processes we use sulfuric acid, and afterwards we can recover the metals with different processes like solvent extraction, ion exchange, precipitation processes to regenerate metal concentrates that can go back to the battery production. And then there are two further options with a lower TRL level, like biometallurgy and direct processing. In biometallurgy, I will talk quite a lot today, or give you an insight on that. In general, we use bacteria and fungi to produce acid that can leach the black mass and extract the valuable metals. In direct processes, we relithiate the cathode active materials, so we need to separate anode and cathodes here. release the cathode active material and put it again into a battery. This is especially a very interesting process for production scraps. Well, and now I would like to tell you how we get to biometallurgy here at the Chair of Non-Ferrous Metallurgy. And actually, we developed a completely inorganic process at first. It's called the Ziel process. We started with an inorganic acidic leaching, so very standard. Then we have some organic acid already there, like with the precipitation of oxalic acid, we recover cobalt and nickel as a mixed oxalate. We removed some contaminants, and at the end we also recovered lithium as lithium phosphate, via precipitation. What we have seen there is that the purity of the products obtained is fine for getting back to batteries, so for PCAM production. We could fulfill all the requirements from the EU battery directive with this process, but what we have seen also is that there is quite a high CO2 footprint for the inorganic acidic leaching, because sulfuric acid actually has quite a high footprint. And that was the first thing why we started studying organic acid leaching. And we've seen that this process option is also working, that we also can recover quite high quality products. And what we also have seen that we can do resynthesis of PCAM with these products for example, LFP. And well, with this background now on battery recycling, where we have seen the technological dynamics. So we have quite a fast market development with different cathode materials, with different technological readiness levels. We have high regulatory requirements. And of course, we also need infrastructure and security always for batteries. There is quite a thing going on. And so our thoughts were how to improve battery recycling, how to keep high qualities of the products, but how to reduce the CO2 footprint of these processes. And actually, that brought us to biometallurgy, because we have currently 3 domains of metallurgy. We've already talked about pyro and hydrometallurgy. Hydro is currently the focus in industry because of the high purity options, because of the efficient extraction, and also the suitability for different chemistries, so for different battery chemistries. But of course, you need to consider wastewater treatment. You also need to consider all the impurities you have in there. And so that brought us also to think about biometallurgy. This is quite an eco-friendly form of metallurgy. There is less concern actually about the production of any pollutants, because we always have quite low concentrations of acids, low concentrations of polluting agents. We have quite low operational costs and energy requirements because you have quite low temperatures, like 25 to 26 degrees C. There are high efficiencies of recoveries possible with low concentrations of acids actually, and a minimal use of additional chemical reagents. Of course, you have extended processing duration with bacteria, and also a sophisticated process control measurement, because you need to keep your bacteria at a specific environment. Well, and for biometallurgy, you need to consider, well, a few things like you can see here. For the microorganisms, we have quite a few influences, like, of course, the heavy metals from black mass, like cobalt, manganese, copper, and nickel. You might wonder why we've also got lead in here, but we always find some traces of lead in our black mass, and that is quite important for the microorganisms, so we need to keep an eye on that. And then you have got inorganic compounds, especially also impurities like sulfur, phosphorus, and iron that influence the microorganisms. You also have organic compounds, so we have learned about the bad guys of the impurities, that especially the organic fluorine could influence your microbial growth quite heavily. And then you have, of course, the abiotic factors, so the salinity, or sorry, the pH, the temperature you use. So quite a few things to consider if you need to do biometallurgy. And then the question arises, isn't this absolutely crazy with all these influences? And no, it isn't. Because if we look back like 80, 90 years ago, in copper extraction, bioleaching was already used, and it is still used. So here you have the copper sulfide grain that is attacked from bacteria, especially the Thiobacillus ferrooxidans in this case. And it is used industrially worldwide in big plants. So this is not a small laboratory idea or a small laboratory equipment. It is used in big industrial plants. And so this was also our thought behind. If we could use that for primary production, could we implement it also in secondary metallurgy, so in recycling processes? Well, and actually we have got two different approaches at our lab. The first one is the one-step bioleaching. In this approach, you put your microorganism and also the metal in one bottle actually at the same time at the very beginning, and let the microorganisms grow beside the black mass in this case. This is sometimes a little bit tricky, especially when you have quite high heavy metal contents in there, because of course the microbial growth is hampered through this heavy metal content. And then there's the second approach, the indirect approach. There you just put your microorganism in your leaching medium, and the microorganisms or the bacteria produce the acid. You separate the acid and put in your residual materials, so the black mass, into this acid. So we just use the acid from bacteria to leach this black mass. And what we have shown in our study is that both options are doable. What we can see here is a direct and an indirect approach. And what we could have shown for Gluconobacter oxidans in this case, together with black mass, is that we can reach quite sufficient recovery rates. Of course, we are not near 100 for all elements, we know that, but this is for a first approach a very good result to get out like 60% for quite a lot of the metals. And then we have also tried to have an idea about, is this microorganism influencing our system in general? So we made for Acetobacillus thiooxidans a comparison of the indirect, direct approach and inorganic sulfuric acid, because Acetobacillus thiooxidans is actually producing organic produced sulfuric acid. And so we use the same concentration on inorganic produced organic sulfuric acid and had then look on that. And what we can see here is that we are more or less at the same range. And so we can see that it's not hampering the leaching efficiency. So the microorganisms and also the heavy metal content that we have added, it's more or less the same like when we use inorganic acidic sulfuric acid, sorry. And well, that already brings me to the end of my talk today, and to have enough time for questions if there are some, is that the future of our batteries is circular. And recycling is a key to sustainability. And that is especially important that we already think about the sustainability of recycling processes at the very beginning of the development of recycling processes. it's not an option to develop a full process chain and then think about sustainability measures at each point. That is not the way we should do it. Raw material security determines competitiveness. And yes, of course, that's a point that is very important, especially if we think about the missing value chain currently in Europe. For this raw material security, it's not only primary mining, but also recycling is an option to get at least the strategic independence on other countries and to have a strategic supply with battery materials in battery quality. Technological diversity requires flexible solutions. Yeah, that's a very important point because we can see that there is development in battery chemistries. It's not only LFP and NMC actually. You might already have heard about sodium-ion batteries. You might have heard about solid-state electrolytes. And that's the main point. We have different chemistries in there and our industry needs to cope with all of this. And actually, it's not an option for Europe to have a recycling plant for each different chemistry because we don't have the high amounts of different batteries now, currently. And so we need to have flexible processes to cope with all of these different materials. And well, my last takeaway for you is the cooperation between all stakeholders. That is quite crucial because we need to be integrated throughout the whole value chain to really reintroduce our recycled materials to battery producers and to also talk with the battery producers about design for recycling, for example. So that are main points I would like to mention at the end of this presentation. So thank you very much for the attention, and if there are any questions, I'm very happy to answer that.
Thank you very much for your very interesting presentation. A lot of new information, especially for me that I'm not really into metallurgy, but that's good. Yeah, if you have any questions, I forgot to mention it at the beginning, but please just write them into the chat. I already have collected 2 or 3 questions, so if you have questions, please text them into the chat and then I will collect them. So give me 1 second to share my screen now.
I just stop sharing.
So I have summarized some questions because I think they go together. So what do you estimate the TRL of biometallurgical recycling at the moment, and what is your prediction for the future? When do we see this on a large scale? And the second question is very similar regarding the gaps for lithium battery recycling at the moment.
Yeah, the current TRL for biometallurgy, I would say, is 3 to 4. So we are at the laboratory stage currently. But in future, that could be a very interesting option, especially in combination with, of course, high-speed leaching, I call it, like if you use inorganic acid leaching, because if you have the both options, you can do the critical elements with the high concentrated sulfuric acid leaching and do the less critical elements like with the bio leaching. So I think it's not the one or the other solution. It's like a combined solution in the future. And the major gaps for lithium battery recycling are currently a few ones. I think the most important one currently is also to have a solution for LFP recycling, because we were focusing for like the last 10 years, especially on NMC, because of course nickel and cobalt are highly valuable metals. They also have, of course, a good feasibility, also economically feasibility, but we have not any recycling capacities currently in Europe for lithium iron phosphate batteries. But of course, we need to recycle the lithium, but also phosphate is a critical material, and we currently don't have a solution for that. So I think this is one of the biggest gaps currently. And in future, especially solid-state electrolytes and solid-state batteries, they will be, at least tricky and challenging for the current recycling approaches, because there are new elements in there like zirconium, tantalum, maybe also vanadium, germanium. So quite a lot of elements that are currently not in the focus of the recycling community.
Let's move on. So what can be improved in battery design or primary production with regards to recycling? Do you see options there because I suppose like traditionally it was not meant, the battery was not meant to be recycled from the beginning, right?
Well, actually, maybe it was meant to be recycled, but it wasn't built to be easy recycled, at least.
Okay.
Yeah, well, very good question. Actually, for the battery design, what I see, especially in EVs, quite critical is what you might heard is battery to chassis. So currently we have battery to packs. So we have one big block of batteries actually in our electric vehicles. And at the end of the lifetime, actually we can just unplug it and move it out of the car. But for in the concept of battery to chassis, it isn't like that. You have single battery modules there that are located in the car at different places in the car to have a good feeling for driving, as to have a good acceleration and to have a smooth acceleration at least. And well, so just for the performance thing. And that is really tricky for us because you need to remove everything before you get to the battery from the EV. So that it's a very tricky thing, and I think this is a design thing.
And then if you look at the battery design itself from the inside, is there something that could be done?
Yeah, it is. Especially we'll look to the future. If we look to solid state batteries, there are different options for solid state electrolytes. And actually, there are oxidic ones that might be, well, easy or at least good integratable to current recycling streams, because also the cathode material is an oxidic material. So at least you're in the same chemistry group. But what we also see is that there are sulfidic electrolytes that could be quite challenging, especially for hydrometallurgical processes. We might need some roasting processes before that might really be complex in future. And what we also see are like coatings, and especially fluorine coatings are currently the newest development. Very good for battery stability and so on, but very bad for recycling actually.
Okay, thank you very much. I have a last look into the chat, but I think we have answered every question. Thank you for your time. Thank you for the very interesting topic.
Thank you for listening.
Thank you. And with that, I wish you all a very nice evening. Have a good Christmas break and a good start into the new year. And I hope to see you then also in the new year in our Triple N Talks again.